When rain begins to fall, it looks simple. Drops from the sky, soaking the ground, filling our rivers. But beneath that familiar scene, something remarkable happens. Every drop triggers a chain reaction, a pulse that spreads across the land. It decides how much water we receive in our rivers when it rains, how fast rivers rise, and how floods form. That pulse is called the catchment response, nature's heartbeat during and after the rain. In this video, we will explore how catchments respond to rainfall and uncover the key factors that influence it. A catchment response is simply how an entire landscape reacts to a rainfall event. It has three key dimensions: magnitude, speed, and pathways. Together, they define how rainwater moves through our catchment. The magnitude shows how much water the catchment sends downstream. We describe this using the runoff coefficient, a measure of how much rainfall escapes as surface flow rather than infiltrating into the ground. It's what shapes the height and volume of the hydrograph, the signature curve of a storm's impact. The speed tells us how fast the catchment reacts. We measure this with terms like time to peak and time of concentration, which tell us how quickly rainfall becomes runoff and reaches the catchment outlet. And finally, the pathways, how water gets there. Some flows rush across the surface, others slip through shallow soil layers, and some travel deep underground as a slow-moving groundwater flow. But why does one catchment respond in minutes while another takes hours or days? It comes down to two forces: the character of the catchment and the nature of the storm. Let's explore them. First, the catchment characteristics, the static features written into the landscape itself. For example, the size or even the shape of a catchment matters. Compact basins focus flow faster than long, narrow ones, concentrating water at the outlet more rapidly. A steep catchment gives rain little time to rest. Gravity pulls it fast, leading to sharp, high runoff peaks. Soil, geology, and surface type are also important. Impervious surfaces repel infiltration, producing more runoff, while pervious surfaces such as sandy soil absorb it, letting water down to the ground. Vegetation, on the other hand, slows the flow. Forests and grasslands catch rain, let it infiltrate or evaporate later, which reduces the runoff peak and volume. But when vegetation is cleared through deforestation or urbanization, the land loses its natural buffer. Then come the event characteristics, the dynamic factors of each rainfall event. A short intense downpour can overwhelm the soil's capacity to absorb water, forcing nearly all of it into surface runoff. Meanwhile, long gentle rainfall might soak deeper, delaying the response. And finally, the antecedent conditions, how wet the land was before the storm began. If the soil is already saturated, even a light rain can trigger heavy runoff. So next time you see a river rise after rain, remember it's not just the storm you are watching, it's the entire catchment, the slope, the soil type, the vegetation cover, and the storm characteristics, all working together in a dance of physics and nature. Understanding that physics helps us to predict floods, manage our water resources, and plan our cities wisely. And this is just the beginning. In the next videos, we will explore the practical aspects of catchment response. First, we will focus on the time of concentration and the methods to estimate it, especially the kinematic wave formula. We will then step inside the RORB, a hydrological model, to see how changing influencing factors such as catchment shape or slope or rainfall temporal patterns can change the entire catchment response. Once we understand how a catchment works, we don't just measure flows, we anticipate them. Stay tuned.